Good evening all. So today let us just see the let us discuss about the AC circuits. In particular, let us discuss about the purely resistive, purely inductive and purely capacitive circuit and the behavior of series RL circuit, series RC circuit and series RLC circuit. So we are going to discuss about AC circuits. So basically, what is the difference between AC and DC? So DC will be having a constant value irrespective of time. So say for example, if the DC is going to have a value of 5 volt, doesn't matter, even if the time tends to infinity, the same 5 volt is going to be maintained. But alternating current, that is AC, is going to vary with respect to time. So say for example, the AC waveform can be a rectangular waveform or it can be a triangular waveform or it can be a sinusoidal waveform and so on. So in our practical use, we are using the AC sinusoidal source in our day-to-day life. So if you take a sinusoidal input, so we can just take the magnitude V of t along the y-axis and the time period in millisecond along the x-axis. The time that is taken for one complete cycle, that is comprising of a positive and a negative cycle, is said to be one complete cycle. So this is the time taken for one complete cycle. So what is the relationship between time and the frequency? First of all, how do you define frequency? Frequency is number of cycles per second. So here, if this is taken to be one complete cycle, then how many such cycles can be accommodated within a second? So the standard frequency is 50 Hertz in our country and in developing countries. And in developed countries, it is 60 Hertz. So the relationship between time period and the frequency is they are inversely related with each other. So time period is equal to 1 by f or f is equal to 1 by 2. Then if you take the waveform, the magnitude of the wave changes from time to time. So it reaches its peak value. It starts at 0, reaches its peak value, then process the 0 to change from positive half cycle to the negative half cycle, and it completes its cycle. This is how. So it has a positive peak and a negative peak. So if it is of 230 volt, then positive voltage is plus 230 volt and negative voltage is minus 230 volt. And we use the RMS values in the calculations. And now let us see how the circuit behaves when a resistor is connected individually across an AC source. So-called purely resistive circuit. So let us take a resistor. Let it be R and let us connect it to a voltage source V. So before that, let us have the discussion about the representation of AC quantities. So say for example, when you take a voltage V of t, it is represented as Vm into sine omega t plus theta, where omega t is the peak value. Omega is the radiant frequency. And theta is the phase angle. So this kind of representation is called as sinusoid. It is not necessary that the sinusoid should always be a sine. So it is not necessary. It can even be a cos term or a sine term. The ultimate concept is that sinusoid will be giving us the detail about the peak waveform, radiant frequency, and the phase angle. If the peak value and the phase angle is taken, and if it is represented, then we call it as a phasor. So the representation of a phasor is P with a bar above. So it is EM angle theta. So this is how we represent the phasor. Or in other words, we can say that the polar representation of a complex number can also be called as a phasor. So while we had been discussing about the DC, we were handling with the real numbers. So henceforth, since we are going to involve both the reactive elements like inductor and capacitor also in the calculation, no more we are going to have the real values alone. So everything, impedance, voltage value, current value are going to be complex. So if you take impedance Z, where impedance is the opposition offered for the flow of current, in general, it can be represented as R plus Jx, where R denotes the resistance value and this Jx in general denotes the reactance value. That reactance can be either an inductive reactance or a capacitive reactance or the net reactance due to the combination of both. So now let us move on to observe the behavior of a purely resistive circuit when connected to a voltage source. So now we have taken a resistor R and connected across a voltage source. Let the voltage be V angle 0 and let us take the current to be I. So now the impedance is equal to R and the current is equal to V by R. And coming to the phase diagram, phasor diagram is that which gives a pictorial representation of the various parameters involved in the circuit. So by seeing the phasor diagram, one can predict what type of circuit it is, whether is it an RL circuit or whether is it an RLC circuit, whether the current leads the voltage or lag the voltage, what is the magnitude of the resistor voltage and the reactive elements voltage, and what is the phase angle between supply voltage and the supply current. Everything can be predicted very clearly on looking the phasor diagram. So to be simple, it is the pictorial representation of any given circuit. So coming to this purely resistive circuit, the voltage across the resistor can be taken as V is equal to I into R. And the current I that is flowing through the circuit will be in the same direction as that of the resistor voltage. Here, the supply voltage is equal to the resistor voltage. And we mean to say that current is in phase with the voltage. So if you take the voltage, current is in phase with the voltage. So the bigger waveform denotes voltage and the smaller waveform denotes the current. So this is V and I, and this is the time period in millisecond. So it means that voltage and current are starting at the same point, reaching their positive peak at the same time instant, and crossing the zero for moving to the negative half cycle at the same time instant, and finishing the cycle at the same instant. So this is what we mean to say as the in phase. Now coming to the purely capacitive circuit. purely capacitive circuit. Let us just take a capacitor. Which is connected to a voltage source. So the reactance of the capacitor is taken to be minus J XC, and let the voltage be V angle 0. And let the current flowing through that be I. So now the impedance can be given by minus J XC, where XC is equal to 1 by omega C. It is minus J divided by 2 pi F into C. Then when you go for the current, I is equal to V divided by minus J XC. And that is how the current will be having a 90 degrees. So if it need to be represented, it is V angle 0 divided by XC with an angle of minus 90. So that is equal to I with an angle of 90 degree. So compared to voltage, the current will be leading by an angle of 90 degree. So the current leads the voltage in case of purely capacitive circuit. So this is the phasor diagram. So it means that before the voltage reaches the maximum, the current reaches the maximum 90 degree ahead. So that is the idea we get out of this behavior. Then coming to the purely capacitive, purely inductive circuit. So let us take an inductor which is connected across a voltage source V, which is of V angle 0. Let the current be I, and the reactance is JXL. So Z is equal to JXL, where it is equal to J into omega L, which is J into 2 pi L, 2 pi into FL. So now the current I can be given by V divided by Z, where it is equal to V angle 0 divided by XL with an angle of 90 degree. So thereby it is I with an angle of minus 90. So if you take the phasor diagram, so V and the current I is lagging by an angle of 90 degree in case of purely inductive circuit. So in purely resistive circuit, voltage and current are in phase. In purely inductive circuit, the current is lagging behind the voltage by an angle of 90 degree. And in purely capacitive circuit, the voltage is lagging behind the current by an angle of 90 degree. So current leads the voltage in capacitive circuit, current lags the voltage in inductive circuit, and current is in phase with the voltage in the purely resistive circuit. So I hope you might have got some basic idea regarding the behavior of purely resistive, purely inductive, and purely capacitive circuit. Now, let us move to the discussion of series RL circuit, series RC, and series RLC circuit. Okay. So now let us have a discussion with the regarding the series RL circuit. So coming to series RL circuit, let us take the resistor R and the inductor in series, which is connected across the voltage source V angle 0. So the resistor is mentioned by R and the inductor, and let I be the current that is flowing through the circuit. VR is the voltage across the resistor, and VL is the voltage across the inductor. So what will be the impedance equation? Impedance equation is equal to R plus JXL, where XL is equal to omega L, which is equal to 2 pi F into L. Then modulus of Z can be obtained by root of R square plus XL square. Then determining theta value, it is tan inverse of XL by R, where this theta is the angle between voltage and the current value. Now, as per Ohm's law, current I can be given by V by Z. That is V divided by R plus JXL, or magnitude of V by modulus of Z with an angle theta. Then, once after determining the value of current, we can determine the value of the individual element drops, that is VR, where VR is equal to I into R. And the drop across the inductor can be given by VL, which is equal to I into XL. So the net voltage can now be expressed in terms of the individual voltage drops, such that P is equal to VR plus JVL. So taking the impedance values, we can construct an impedance triangle taking R along 0 and XL along a 90° with respect to R, and the hypotenuse joining this will be the modulus of Z. And it is theta, which is subtended between the resistor R and the hypotenuse. So thereby, we get cos theta is equal to R by modulus of Z. So this is the power factor, where the power factor ranges from 0 to 1. When the power factor is closer to 1, it means that the transmission is efficient and the losses are less, and the power that has been transmitted from the sending end is maximum reaching the receiving end. If the power factor is closer towards 0, then it shows that much of the power has been wasted in the losses and the transmission is not that much efficient. So always we strive to improve the power factor. And now we can also construct a voltage triangle taking the individual voltage drops. VR is always taken along the 0° and VL is taken along the 90° with respect to VR, and the hypotenuse is the supply voltage. So even using this, there is a possibility for us to determine the value of theta, which is equal to tan inverse of VL by VR. So this theta and the theta, which is taken in terms of XL and R, everything means the same, which refers to the phase angle between voltage and current. And then if we need to determine the value of power, of course, the power is a complex power, which is denoted by P plus JQ. So where P is equal to modulus of V into modulus of I into cos theta, where V and I are RMS values, and real power is measured in watt. Q is the reactive power, where V and I are, where it is equivalent to V into I sin theta measured in volt ampere reactive. Then S is the apparent power, which can be given by root of P square plus Q square, or modulus of V into modulus of I, which is measured in volt ampere. So now, right from the beginning, we have been just seeing what is the impedance, what is the magnitude of the impedance, and what is the phase angle, how to determine the value of current, what is the voltage drop across the individual element R and L, then how to construct a voltage triangle and impedance triangle based on the equations. And finally, we have just seen the power. So it is the real power P, which we are experiencing in our day-to-day life. Now, coming to the phasor diagram of series RL circuit, let us take VR along 0 degree and the current I is always along VR, which is in phase. Then VL is drawn at 90 degree between VR and VL. Then the supply voltage is the resultant of VL and VR. So the angle that is subtended between the supply voltage and the supply current is taken to be theta. So this is the phasor diagram for the series RL circuit. Then coming to the series RC circuit. So let us take a resistor in series to a capacitor where the voltage is connected across. So voltage V is taken to be V angle 0 and the resistor is taken to be R and capacitor is taken to be C. And I is the current that is flowing through. So V is equal to V angle 0. And VR is the voltage drop across the resistor. And C is the VC is the voltage across the capacitor. So now let us take the impedance. The impedance equation is equal to R minus JXC. And modulus of Z can be given by root of R square plus XC square, where theta is equal to tan inverse of XC minus XC divided by R. So I is equal to V divided by Z. So where Z can be given by Z minus JXC, or it can also be equivalent to modulus of V divided by modulus of Z with an angle theta. So here the angle theta will be in the negative direction. And once after determining the value of I, there is a possibility for us to determine the value of VR. So VR is equal to I into R. So VL is equal to, VC is equal to I into XC. So once after determining the value of VR and VC, we can get the value for V as VR minus JVC. As we have constructed the impedance triangle and the voltage triangle for the previous case, similarly we can construct the impedance triangle over here. So resistance can be taken along 0 and XA can be taken along minus 90 degree with respect to R, and the impedance is modulus of Z. So this is the impedance triangle. Then coming to the voltage triangle, same way, VR can be taken along this 0 and BC can be taken along 90 degree. And supply voltage can be taken along this, along the hypotenuse. Then as we have determined the value of real power, reactive power and apparent power, the same power equations hold good for all types of circuits, irrespective of the elements that are connected in it. So real power can be given by modulus of V into modulus of I cos theta, where V and I are the RMS values. And the real power is measured in watt. And the reactive power Q is given by modulus of V into modulus of I into sine theta, which is measured in var. And then apparent power can be given by modulus of V into modulus of I, which is given by volt ampere. So now coming to the phasor diagram. So we have to take VR along 0 degree, and the same way I will always be in phase with the resistor voltage drop. Then VC is taken along minus 90 with respect to VR, and the resultant that is drawn to VC and VR is the supply voltage V. And the angle that is subtended between the supply voltage and the current I is taken to be theta. So here the power factor is leading in case of capacitive circuit, and the power factor is lagging in case of inductive circuit. So power factor is lagging. And in inductive circuit, I lags the voltage, and in series RC circuit, I leads the voltage. So that is the idea regarding the series RC circuit. So next, let us discuss about the behavior of series RLC circuit. Coming to the series RLC circuit. So let us take R, L, and C in series, which is connected across a AC voltage, which is of V angle 0. So let this be R, L, and C, and let the current be I, which circulates through the circuit. And VR is the drop across the resistor, and VL is the drop across the inductor, and VC is the drop across the capacitor. So what will be the impedance equation now? It is R plus JXL minus JXC. And what will be the modulus of Z? So we get the modulus of Z by taking square root of R square plus XL minus XC. And here, depending upon the value of the reactance, so we can rewrite this as R plus J into XL minus XC. And based on the value of the reactance, it results in 3 cases. Either XL can be greater than XC, or XC can be greater than XL, or XL is equal to XC. So first let us come to case 1. In case 1, let us take XL is greater than XC. So in which case, the modulus of Z is given by root of R square plus XL minus XC the whole square. And theta can be given by tan inverse of XL minus XC divided by R. So once after we determine this, I can be given by V divided by Z or modulus of Z divided by modulus of V divided by modulus of Z with an angle theta. Once after determining the value of I, we can get the voltage drop across the element VR, where it is equivalent to I into R, and the inductor voltage VL, which is equal to I into XL. Similarly, VC, which is equal to I into XC. Then we can represent the supply voltage V as VR plus J into VL minus VC. So modulus of V can be given by root of VR square plus VL minus VC the whole square. Coming to the impedance triangle, same way, we just take the R, then XL minus XC is taken along the 90 degree. Then the impedance triangle is drawn with the impedance, modulus of impedance as the hypotenuse and theta. Then the same way as we have determined the value of power, we will be able to get real power as modulus of V, modulus of I, cos theta, which has a unit of watt. Then Q is equal to V into I sin theta, and S is equal to V into Y volt ampere. Coming to the phasor diagram, we have to draw VR, and IR is always in phase with VR. So draw in the same in phase. Then VL is more as XC is greater in magnitude. So VL will be drawn with an angle of plus 90 degree in the positive direction. Then VC is drawn at an angle of minus 90 degree with respect to VR. And we need to take the resultant VL minus VC, and the supply voltage is drawn as a resultant of VL minus VC and VR. So the angle between the supply voltage and current is theta. So this is case 1. So coming to case 2. XC is greater than XL. So in which case your modulus of Z will be root of R square plus XC minus XL the whole square. Then I can be determined with V divided by modulus of Z or modulus of V divided by modulus of Z with an angle theta. So theta can be given by tan inverse of XC minus XL divided by R. So once after determining the value of I, we will be able to calculate the individual drop across the elements. So VR can be given by I into R, and VL can be given by I into XL, and VC can be given by I into XC. Then the supply voltage can now be written as VR minus JVC plus JVL. And modulus of V can be given by root of VR square plus VC minus VL the whole square. And we can draw the impedance triangle such that VR is taken along 0 and XC minus XL along VR with an angle of minus 90 degree, and the hypotenuse which is contributing the value of modulus of Z. And in all the circuits, cos theta will be given by R by modulus of Z, which gives a measure of power factor. Then the real power, reactive power, and apparent power can be calculated with the same equations as we have seen for all other circuits just before. Then, coming to the phasor diagram. VR is drawn along 0 degree and the current I will always be in phase with VR. VC is drawn with an angle of minus 90 degree with the VR, but the magnitude of VC is greater as XC magnitude is more compared to that of XL. Then VL is drawn in the positive direction with an angle of 90 degree with respect to VR, but the magnitude is lesser as per the magnitude of XL. Then the resultant VC minus VL is taken along the negative direction, and the resultant for this VC minus VL and VR is the supply voltage. The angle that is subtended between V and I is taken to be the theta, which gives a measure of the phase difference between the supply voltage and the supply current. So that's it regarding the second case. So coming to case 3. That is equal to R plus J XL minus XC, where XL and XC become 0 as they are equal in magnitude and opposite direction. So thereby I is maximum given by V divided by R. And we can also calculate the value of VR as I into R, VL as I into XL, and VC as I into XC. Then coming to the phasor diagram, the VR is taken along 0 degree and the current I will be maximum. VL will be taking along 90 degree with respect to VR in the positive direction, and VC is taken along VC is taken in the negative direction with an angle of minus 90 degree with respect to VR. But VL and VC are equal in magnitude and they cancel each other as they are exactly 180 degree opposite. And this is the phasor diagram of case 3. So in first case, I lags the voltage and the power factor is lagging power factor. In second case, I leads the voltage and the power factor is leading power factor. And in third case, I is in phase with the voltage and the power factor is unity. So I hope now you might have understood clearly the behavior of the circuits. When you have the series RL circuit, series RC circuit, and series RLC circuit. So now let us have a discussion regarding the three-phase and three-phase circuits. So coming to three-phase circuits, just an idea that the three-phase circuits are two in classification. One is a star connection, another one is delta connection. In star connection, so coming to the three-phase circuits, there are two types of connection. One is a star connection and another one is delta connection. In case of star connection, we will be having the load in the form of a star. That is, you will be having a common neutral point. You will be having a load and three phases of load. So R, Y, B. So R load, Y and B. So if you look at this point at which all the three phases are connected is said to be the neutral point. And this is the star type of load. Coming to the delta, it is in such a way that we will be having a triangular like structure for a delta load. So if you have this to be R, Y, B, R, Y, B, then you can represent this as ZRY, ZYB, and ZBR. So these are the two types of load connections we have in case of the three-phase circuits in a balanced circuit. And coming to the equations, before that, it is very essential for us to know that if it is a single phase, we will have a phase wire, one neutral wire, where the rating of voltage is single phase 230 volt 50 Hertz AC supply. In case of three phase, we will be having three such phase wires where R, Y, B are those three phase wires given the different color codings to differentiate one phase from the other, and we have a one neutral wire. If we have this type of connections, we say it as a three phase four wire connection. So if we have only the three phase wires, then we say it as a three phase three wire connection. Now, the measurement of voltage between any two phases is called as line voltage, and the measurement of voltage between a phase wire and neutral is called as phase voltage. So generally, the line voltage will be greater than the phase voltage. The phase voltage ranges the value of 330 volt, and line voltage will be 415 or 440 volt. So coming to the relationship of star and delta, line voltage will be √3 times phase voltage, and line current is equal to phase current. Whereas in case of the delta connection, line voltage is equal to phase voltage, and line current is equal to √3 times phase current. And coming to the power equations, since it is a balanced load, we take the real power, phase voltage into phase current multiplied with cos phi gives the single phase power. So if we do a single phase power measurement and multiplying it with the 3 will give us the three phase power. It is given as what? Coming to reactive power, phase voltage multiplied by phase current and sin theta into sin theta will give the single phase reactive power, which is measured in bar. And when it is multiplied with the 3, we will be able to get Q. Coming to apparent power, Vp, Ip, which gives a single phase apparent power. And when it is getting multiplied with the 3, we get the three phase apparent power. So it is very essential that the multiplication factor is 3 when we are using the phase values, whereas when we are using the line value, it is √3 Vp Ip cos theta for P, and for Q it is √3 Vp Ip sin theta. Then for S, it is √3 VL IL cos theta, √3 VL IL sin theta, and √3 VLIL for apparent power. So the power equations will be the same irrespective of the connections. And very important thing to be noted is the relationship between the line and the phase values. So I hope I have given you a clear explanation about the various types of connections under AC circuits. Thank you.